Hello bachcho, today we will move on to our next topic of the same chapter, which is comparison of charge and mass. And after that we will cover three more topics, which are charging of a body, Coulomb's law and its limitations.
Comparison of charge and mass. Electric charge can be positive, negative and zero, but mass is a positive quantity. The second difference can be electric charge doesn't depends on the velocity of the moving object, but mass depends. As velocity of the moving object increases, the mass of the body will also increase. According to the relation mv is equal to m0 upon under root 1 minus v square by c square, in the relation mv is the mass of the object at velocity v, m0 is the rest mass of the object, that is mass of the object when it is at rest. V is the velocity of the object and c is the speed of light, which is equal to 3 into 10 to the power 8 meter per second. When velocity of the moving object is much less than speed of light, the ratio v square by c square will be much less than 1, and hence there will be no effect of subtracting such a small quantity from 1, and the denominator will remain 1. Therefore, the mass of the moving object at velocity v will be equal to the rest mass. In case when the velocity of the object is tending to speed of light, that is the velocity of the object is approaching to 3 into 10 to the power 8 meter per second, the ratio will tends to the value 1. In that case, denominator can have the value 0, and hence the mass of the moving object at velocity v will be equal to infinite, or it may be infinite. It is not possible because no object can get such amount of energy to approach the velocity which is equal to or which tends to speed of light. So in general, we consider mass of the moving object at velocity v as its rest mass. The next difference is electric charge is quantized but mass is not quantized, that is mass can have the rational values also. Electric charge is conserved but mass is yet to be conserved. According to Einstein's relation E is equal to mc square, mass can be converted into energy. Therefore, its conservation law is yet to be established. Next, force between two charges can be attractive and repulsive both, but the force between two mass is always attractive. Charge can never exist without mass, but mass can exist without charge. Our next topic is charging of a body. This can be done by three methods. First is charging by rubbing, second is charging by conduction, and last is charging by induction. In first method, that is charging by rubbing, two uncharged insulating bodies rub against each other. By doing so, electrons of the body gain energy and get transferred to another body. The transfer of electron occurs from the body in which electrons are held less tightly to that in which electrons held more tightly. In this process, the body which gives electron becomes positively charged and other which gains electron gets negatively charged. Second is charging by conduction. When one charged body put in actual contact with an uncharged body, some charge transfer to the uncharged body. In this process, both the body becomes likely charged. Third one is by induction. In this method, when an uncharged body placed very close to a charged body without touching, the nearer end of uncharged body acquires opposite charge. This is called charging by induction. In this method, the uncharged body get polarized. Here the meaning of polarization is it is the process of separating opposite charges within the body. By doing earthing the rear end of the uncharged polarized body, keeping the charged body near it, the rear charges neutralize due to earthing. After removing earthing and then charged body, polarized body will get oppositely charged, and hence redistribution of charges occur on the uncharged body. In this chart, the three methods of charging of a body is shown by figure, and in upcoming slides, the three methods of charging of a body is explained by video.
Topic: Electric charge. How does a plastic comb attract paper? What? You don't believe me? Okay, let us try. Take a plastic comb and bring it close to some pieces of paper. Hey, wait, don't laugh. We need to do something first. Rub the comb on your dry hair and then bring the comb close to the pieces of paper. See? I was correct. The pieces of paper got attracted to the plastic comb. Do you think it is magic? No. The reason behind this is electric charge. Electric charge is the quantity of electricity held in an object. There are two types of electric charges, positive and negative. However, there are some objects where the positive and negative charges are equal to one another. In such cases, we say that the object is electrically neutral. So, was the plastic comb initially electrically neutral or electrically charged? Initially, the plastic comb was electrically neutral. That means it had an equal number of positive and negative charges. Hence, it did not have the ability to exert a force and attract the pieces of paper. So, after rubbing the plastic comb on our dry hair, why was it able to attract the pieces of paper? I will tell you why. When we rubbed the plastic comb on our dry hair, it gained an electric charge. Once it got electrically charged, it got the ability to exert a force on the pieces of paper and attract them. This charge is called as static electricity. However, do you think, like a plastic comb, a metallic comb would also attract the pieces of paper? Nope, you are wrong. A metallic comb will not attract the pieces of paper like the plastic comb. Wondering why is that so? It is because plastic is not a good conductor of electricity. It does not allow the electric charges to flow through it onto the earth. As a result, the charges build in the plastic comb, making it electrically charged and enabling it to attract the pieces of paper. However, metal is a good conductor of electricity. It does not let the charges build in it. It allows the electric charges to flow through it onto the earth, thus not allowing the metallic comb to get electrically charged. As a result, the metallic comb does not attract the pieces of paper.
Charging by conduction. Bodies can be charged by contact, that is, by the method of conduction. By conduction, the body acquires the same charge as on the charging body. Charging a body by conduction can be understood by doing the following activity. Charging a paper cylinder by conduction. Make a paper cylinder by rolling a strip of paper on a pencil and then gently pulling out the pencil. Suspend the paper cylinder by a thread tied to its center. Now, touch the paper cylinder with a glass rod rubbed with silk so it has a positive charge. Remove the glass rod and then again bring it near the paper cylinder. What happens? The paper cylinder is repelled by the positively charged glass rod. Next, bring an ebonite rod rubbed with flannel, negatively charged, near the paper cylinder. What happens this time? We can see that the paper cylinder is attracted by the ebonite rod. This means that the paper cylinder has acquired a positive charge, that is, the same charge as on the glass rod due to conduction. So it repels with positively charged glass rod and attracts with negatively charged ebonite rod.
Sphere mounted on an insulated stand. A negatively charged rod is brought close to one end of the conductor. This end of the conductor gets positively charged due to induction. The opposite end of the conductor gets negatively charged. When the negatively charged end of the conductor is touched with the finger, the negative charge flows out and the only positive charge remains on the sphere. As soon as the finger is removed away, the positive charge gets evenly distributed uniformly all over the sphere. Now, there are two conducting spheres placed on insulated stands. A negatively charged balloon is brought close to one of the conducting spheres. This induces positive charge on the closer sphere and the negative charge on the rear sphere. When the sphere with the negative charge is removed away from the positively charged sphere, the negative charge gets evenly distributed on the sphere. When the negatively charged balloon is removed away, the positive charge also gets uniformly distributed over the concerned sphere. Look at one more example. A positively charged glass rod brought close to an uncharged conductor. This induces an opposite, that is, negative charge on the closed end of the conductor. The opposite end gets induced with the positive charge. With the positive end of the conductor is earthed. The electrons from the earth flow in and neutralize the positive charge. The charged glass rod is now removed and the negative charge gets uniformly distributed on the conductor. This is electrostatic induction.
Next topic is Coulomb's law, and which is very important topic of this chapter. This law gives an idea about the electrostatic force between 2-point charges. Here the sense of the point charge is that the size of the charged bodies is very small as comparison to the distance between them. The statement of Coulomb's law states that the magnitude of the electrostatic force between 2-point charges is directly proportional to the product of the magnitudes of the charges and inversely proportional to the square of the distance between them. That is, electrostatic force is directly proportional to the product of the two charges, which is Q1 and Q2, their magnitude only, and inversely proportional to the square of the distance between them, which is R. After removing the proportionality sign, there comes a constant K. This constant K is known as electrostatic constant.
The electrostatic constant is equal to 1 by 4 pi epsilon naught for charges situated in free space. Here the sense of free space is air or vacuum. The value of 1 by 4 pi epsilon naught is equal to 9 into 10 to the power 9 Newton meter square per Coulomb square. Here epsilon naught is absolute electrical permittivity of the free space, which is equal to 8.85 into 10 to the power minus 12 Coulomb square per Newton meter square. There are much similarities in Coulomb's law and Newton's gravitation law, which I have mentioned here. You can go through this topic.
There are some limitations of the Coulomb's law, as Coulomb's law is only valid for point charges which are at rest, that is, we cannot apply Coulomb's law on the charges in motion. And there is also some difficulty to apply the Coulomb's law on the charges which are in arbitrary shape. In that case, we will not able to determine the value of the distance between the two charges. And last is, this law is not applicable where the inverse square law is not valid.
So homework is, you have to read out gold leaf electroscope and conductors and insulators with examples from your textbook, and you have to learn the values, that is numerical values of electrostatic constant and absolute electrical permittivity of free space with unit and dimension. Thank you.